Welcome to Texas State University's Chemistry 2330 Introduction to Organic Chemistry. I'm your guide, David Irvin, and we will continue with Chapter 3, Part 3, Alkanes and Cycloalkanes. Okay, so we're going to continue on looking at the UPAC system for naming things, and we're going to further define our hydrocarbons here. Okay, so if we look at our IUPAC name, the general system is we have a prefix, an infix or main, and a suffix, which tells us the class of the compound. So the prefix tells us the number of carbon atoms in the parent. The infix tells us the nature of those carbon-carbon bonds, okay? And then the suffix tells us the class of the compound, okay? So the way we'll be using this is when we have only single bonds associated with a common, we'll have the AN, like in hexane, right here. If we have one or more double bonds, we're going to use the ene, as in ethene. Or if we have one or more triple bonds, we're going to use ine, as in alkyne. So let's talk about all the different prefixes and suffixes we can have. Okay, so now that we have the infix, which tells us the nature of the carbon-carbon bonds, whether we have a single bond, a double bond, or a triple bond, the suffix actually tells us a little bit about the class of the compound or the functional group allowed to it. So the suffix, in the case of a hydrocarbon, the suffix would be an E. So hexane, the AN is the infix and the E is the suffix. That tells us that we have a hydrocarbon and there's no other type of functional group available to it. If we have hexane and we drop the E at the end and add OL, we would have an alcohol. So it'd be hexanol, which would tell us that we have a different functional group than just carbon-hydrogen bonds. If we have an aldehyde, we can drop the E and add AN, hexanal, right there. If we have a ketone, we drop the E and add ONE, hexanone, right there. And the last set we'll do is when we drop the E and add oic acid for hexanoic acid, okay? So the prefix tells us number of carbon, hexa. The infix tells us the type of carbons. Ane is single bonds, ene is double bonds, ine is triple bonds, and the last letter at the end tells us whether it's just a hydrocarbon or some other functional group. So this follows through all of the different compounds we'll be going through in the entire semester. So, and we'll have different priorities for different groups, okay? So let's go over that one more time. So in this first compound here, we have a total of 1, 2, 3 carbons. So that means prop is our okay. So let's use all those again. And here in this first compound we have 1, 2, 3 carbons in it, which means we have prop as our suffix. So that's the number of carbons we have. We have at least one double bond in the system. So that means our infix here is ene, right here. And we have no other functional groups. So our suffix here is the E, telling us we just have carbons and hydrogens in the system. So prop is number of carbons. Ene tells us we have a double bond. And the E at the end tells us we only have carbon and hydrogens. So suffix, infix, and prefix, infix, and suffix. Okay, so let's look at this compound right here. We have, I'm going to change colors here. We have 1 and 2 carbons, but we have an OH at the end. The OH at the end tells us an alcohol, and so we have to drop the E and add OL. Okay, so if we look at how many carbons we have 2, so that's ethyl right here. But we have no double bonds here, so our infix is the AN. So we have ethanol. Ethanol is our IUPAC name associated with it. Okay, let's move to the next one right here. And we have for this one, we have 1, 2, 3, 4 carbons. So that's going to give us bute for the 4 carbons right here. We have no carbon-carbon double bonds, so that gives us an AN for like an alkane, but we have a carbonyl here. And this carbonyl has a carbon bonded to this side and a carbon bonded to this side, which turns it into a ketone. That's one of the functional groups we talked about on the last set of slides. And so we have ONE at the end. So our prefix is our number of carbons, bute. Our infix is the fact that we don't have any double or triple bonds, and own tells us we have a carbonyl with 2 carbons bonded to it. So it's butanone, butanone, okay? So let's look at this compound now here. We have 1, 2, 3, 4 carbons, so we have bute again. We have a carbonyl, but it has a hydrogen bonded to it. That turns it into an aldehyde. So we have al at the end of the word. So we have no double bonds between any of the carbons. So we have butanal, butanal. Now let's take this and take this off here and turn it into a carboxylic acid, butanoic acid, because there's no double bonds here. Ooh, let's apply that rule to a cyclo group here. We have a cyclo group with an alcohol pendant to it. So we have cyclohex. We have no double bonds, so it's AN, and we have an alcohol at the end, so it's O. Cyclohexanol right here. Ooh, 2 carbons, so that's going to give us F right here. We have a triple bond, so that changes to a YN. And we have no other functionality to it. We only have carbons and hydrogens, so that gives us an E at the end. So that's ethine right here. Ooh, let's do this last one right here. We got 2 carbons available to us, so that gives us F. We have no double bonds, so that's going to be an AN, and we have an amine at the end, so that's going to be ethanamine. So we'll be able to apply these prefix, suffix, and infix to give us the idea of every little component within that carbon so that it has a nice systematic method. Okay, so now that we have the basis for our system, let's talk about different possible conformations that we have. Okay, when we have a compound like this alkane right here, we have an sp3 hybridized carbon bonded to an sp3 hybridized carbon, okay? And the only barrier for these to rotate is where the different substituents might come into interact with each other, which means that if we rotated this and looked at down the carbon-carbon bond such that we were looking at hydrogens here. So imagine we take this and rotate it. So we're starting to look just down the carbon-carbon bonds right here. There's several different configurations we can have it such that we can see where those hydrogens are. And one of the ways we look at this is what we call a Newman projection. In a Newman projection, what we do is we take the carbon that's in front and we draw our nice propeller here. And then the carbon in the back, we get a circle and we draw the propeller here. Now, in the configuration where the hydrogens are separated as much as possible in our Newman projection, we call this our staggered configuration, okay? And that's because all of the hydrogens are as far apart from each other as possible, and therefore we call this our staggered conformation in our Newman projection, okay? Now, with just ethane, we only have a couple different things you can start to rotate around, and so they can actually start to have the hydrogen butt up against each other, okay? So when we rotate that from that staggered position such that those hydrogens are starting to interact with each other, we have what we call the eclipsed projection here. So all we've done is taken these hydrogens and rotated them 60 degrees from that staggered configuration, and we end up with what we call the eclipse configuration, Okay. Now that those hydrogens are eclipsed, they're starting to kind of interact with each other, and that's a slightly higher energy than that, which is why we typically see them tilted in that other position where they're staggered, okay? So that when we draw these, the most energy efficient way to do it is this long chain, fully staggered configuration. That's why most of the time we draw it that way, is this long zigzag. Okay. Does that mean it's like that all the time? No, that is a free rotation. All you need is a little bit of heat to rotate any one of those bonds or multiples of those bonds. So think about it the way is that this is, if you wanted to draw it in its lowest energy conformation, it's going to be this fully staggered, fully extended conformation. Okay, so what makes it more and less energy? Okay, so the thing that makes it more or less energy is as you start to rotate this, the hydrogens don't see each other very much, and when we start to get those hydrogens starting to get close to each other from the staggered position to the eclipsed position, what that does is create what we call torsional strain. A torsion angle is between 3 bonds and 4 atoms. So the angle between this hydrogen, the carbon, and that last hydrogen right here creates a total of 3 bonds over 4 atoms. And this, when these hydrogens are eclipsed, they aren't close to each other. And then as you get them to the eclipse stage, they start to push apart. And this is called the torsional strain or eclipsed interaction strain. And this takes a little bit of energy, about 3 kcals per mole to do, which means in this staggered position, it takes less energy. And then you have to add heat to get it to this eclipsed part. Okay. So what does this mean for cyclo groups? Well, in a cyclopentane, we have, if we looked at the 5 internal angles here, right here, we would want to see it as, because they're tetrahedral, we want them to be at 9.5, 109.5 degrees, but they're not. They can't spread that far out. And so they're slightly less than that at 109, which means that having that being tied into that ring gives it a slight bit of strain. Okay? And so just like we had the torsional strain for the straight chains, when we have rings, we can have ring strain or angular strain. And this means we have to add a little bit of energy to the system to get it to go. Okay, so if we had it completely flat, okay, that would give us a ring that would have about 105 degrees right here to make them all even on the inside right here. But it wants to be 109.5 degrees, okay? But it can't do that. So what it's going to do is it's going to pucker slightly on one side to relieve a little bit of that to go expand from the 105 to the 108. So it's getting closer and closer to being in that string. So what we'll see is in cyclohexanes and cyclopentanes, we actually don't have flat rings, we actually have puckered rings. And in the case of cyclohexane, we call it the envelope conformation. Okay, when we have cyclohexanes, one side puckers up and the other side puckers down. Okay, now cyclohexane is big enough that when one side puckers up and one side puckers down, it actually ends up with 109 degrees, 109.5 degrees on all of them. And so this pucker up, pucker down is what we call a chair conformation. So if you look at it kind of like a lounge chair, you can actually lay across it here. And this is its most stable or lowest energy conformation right here, the chair configuration of the cyclohexane. Okay, does that mean it's like that 100% of the time? No, there are still some bits of freedom there and they can move around. Okay, so once we form this chair, we now actually end up with different hydrogens in different positions. Okay, so in this case here, if we think about this as our cyclohexane chair right here, okay, and we look at, so this is our cyclohexane chair, and we put a line right in the middle of this going up and down, that represents this line here, okay? So if we look at it from the side, that chair, we have hydrogens that point up and down in line with that line, or that axis, that rotational axis there. And then we have different hydrogens that are pointing out and away from. So these are pointing out and away from that axis. Right here are the green ones, and we call those equatorial because they're around the outside, away from the axis. And we call the ones that are in line with that axis the axial hydrogens. And so for these, that would be these three here, and the three ones that are similar to it on the bottom here. Okay, so in this lowest energy chair conformation, we have 3 hydrogens pointing up with the axis, 3 hydrogens pointing down with the axis. And so those are the axial hydrogens. And then we have the remaining 6 pointing out around the outside. Those are what we call the equatorials right there. And so whenever we have a substituent on this ring, we want to try to put it in that equatorial position, if at all possible. Okay, now, like I said before, that is with one puckered up and one puckered down. Okay, what if we wanted to pucker them both in the same direction? Okay, we call that the boat configuration. And so if we look at this structure here, this is the chair configuration that we had before. And if we move this one up right here, we end up getting what we call the boat configuration. So notice that 2 ends of it are puckered up at the same place. Okay, this takes a little more energy because now these hydrogens are starting to butt up against each other, and they're starting to get a little more resistance here. Okay, so well, we can't, if you have enough heat or enough energy in the system, it can form this. These 2 hydrogens now have a special name, because just like on the 2 ends of a boat would be, you would put a flagpole on there. We call those flagpole, or the flagpole hydrogens, and they start to butt up against each other. Notice these are sort of kind of axial, but kind of poking out a little bit, so they're not interacting nearly as much as these 2 hydrogens are here. Okay, so come on, there we go. All right, so because of this interaction, there's more torsional strain on the system, which makes it higher in energy to have it in this configuration. And then there's this steric strain from having those hydrogens butt up against it. So while the boat conformation is available to cyclohexane to flip back and forth, the more stable is, of course, the 1 up, 1 down chair configuration. Okay, so once we start adding these things together and together and together, we want to see how things are arranged and once we have a whole bunch of rings attached together, we start to see that certain things start to start butting up against each other. But in this complex formula here, this particular one is a cholesterol. No, it's a derivative of cholesterol. And it has these 1, 2, 1, oh, lost my hand. 1, 2, 3 cyclohexane rings and a cyclopentane ring all put together. And the way they try to do it is when it hooks together, all of the cyclohexanes are actually in the chair configuration, as you see here. And that is one of the lower energy configurations, to have all of those cyclohexanes in chair configuration, and they're bound, so their substituents are pointing up or down based on that configuration. So that's kind of an interesting thing, that as we build more and more complexity into here, it actually finds a lowest energy conformation possible. Okay. So we started with the chair conformation, and if you pucker one up and pucker one down, that's the chair conformation right here. But what can it, when it can't this side pucker up and that side pucker down? Well, yes, it can. And so we have two possible equivalent chair conformations, and they'll convert back and forth through the boat conformation until there's something different about it. For example, if we have one chair configuration, we have 6 axial and 6 equatorial hydrogens. We go through the boat conformation, which has those 2 flagpole hydrogens, back to having 6 axial and 6 equatorial. We only favor one versus the other when we have something larger than hydrogen as one of the substituents. Okay, so for example, if we have this configuration here where we have a methyl group attached to it here, the methyl group is now bigger than a hydrogen, okay? So because it's bigger than hydrogen, that means it's going to favor the situation where the methyl group is in its equatorial position as opposed to this axial position, because it's going to start to butt up against these hydrogens here. So this is one of the few times where actually one chair conformation is more stable than the other conformation, because we have a larger group than hydrogen on the cyclohexane. That's the only time we'll see a favor of one conformation over the other, is when we start adding large groups to the system.